So what do you think of natural rubber molecule? So it has double bonds. It has allylic hydrogen, allylic carbon, right? And CH3 methyl group and two hydrogens attached to the uh, carbon, which is in the double bond, right? So that is the isoprene molecule, right? So it is a polymer, right? What do you think of this? Do you think it is exactly pure? Pure is polyisoprene. If I say it contains hydroxyl groups, it contains epoxy groups, right? It contains carboxylic groups because this is a natural product, right? It is a natural product, right? There are so many mutations can be there, right? Mutations means not the genetic mutations, right? So normally we think cis polyisoprene is CH2 CH3 double bond CH, right? So CH2 likewise, but that is not, right? There are hydroxyl and there are carboxylic, there are epoxy groups, right? Like different groups are there attached to the main chain of 1,4-cis polyisoprene, right? However, this is a hydrocarbon, right, which is inside or else which is surrounded by a lipid layer and a protein layer, right, and an adjacent water layer, right? This is a particle. Then inside the particle you can see the hydrophobic rubber molecules, right? So why we call this as a colloidal system, right? It is available as colloids. That's why we call it as colloidal system, right? So it is a stable colloidal system. So how does it occur as a stable colloidal system? It is stable. How? Right? That is a problem, right? So we'll see. So there are different types of stabilities. You can see kinetic stability. So kinetic stability means, let's say, to combine two of people, right? Let's say a boy and a girl, right? I argue that they should pass an energy barrier. To make a relationship, they should pass an energy gap. Sometimes that gap is very less, sometimes that gap is very high. If the gap is very high, it is very difficult to build up a relationship. If the gap is very less, so they will merge together very easy. And also, do you know what is the activation energy of a reaction? Activation energy of a reaction, right? These are the reactants. These are the products, right? So to occur products, these reactants should take energy and pass this energy gap, right? If they do not pass this energy gap, we will not take these products, right? That's why kinetic is there, right? So that is kinetics, right? And next one is the thermodynamic stability, right? Thermodynamic stability, right? So that's where we talk about Gibbs free energy. I think you know what is Gibbs free energy. Delta G equals the enthalpy delta H minus the temperature and entropy, right? So to occur a system is stable, right? Right? This delta G should be equal or below 0, right? If this principle follows, that system is more stable, right? Keep those things in your mind, right? When it comes to the latex, right? So let's say think this is a latex particle, right? So here it is a positive charge, right? Don't mess with that, right? Here it is positive charge. If the surface is positively charged, the adjacent next layer is negatively charged, right? To keep the charge balance, right? And also there are positive charges next to that, and sometimes dispersed negative charges may be there, right? So likewise, positive layer, negative layer, right? Then dispersed, right? Ions are dispersed, negative charges and positive charges, right? Because in a system, both are there. Because of the surface potential, right? Surface potential, there is a repulsive force in between, right? There's a repulsive force in between that is called electrostatic stability. Electrostatic stability, right? What does this mean? The steric stability, right? So some cases, right? Let's say we can tether some molecules, right? We can bond some long chain molecules onto these particles, right? That is called tethering, right? We can tether some molecules, right? So when these are there on the surface of these particles, so can they easily merge because of these entanglements and barriers? So they cannot, right? That is called steric stability of an emulsion or whatever system, right? Then how many stabilities in a system? Kinetic, thermodynamic, electrostatic, and steric. So latex particle distribution in the water phase, right? So all the latex particles, those are negatively charged, right? They are available in the water phase, right? In a latex system, right, we can see liquid phase, water phase, and the rubber phase, right? This is the rubber particles are the rubber phase, right? So this rubber phase is available in the water phase, right? Dispersed in the water phase, right? So you can see there are collisions, right, and movements. So particles have some velocity, right? So they have some attraction, right? So those are called van der Waal attraction forces. So there are van der Waal attraction forces in between. And also because of the same charge density, high same charge density, right? So there are repulsions that is called electrostatic repulsion, right? So electrostatic repulsion forces are dominant than the van der Waal attraction. That's why you can see repulsions in between, right? Repulsive forces, electrostatic repulsions are dominant in the system compared to the van der Waal attraction, right? As well as there are the particles has kinetic energy, so they have a velocity, right? So they can move in different directions, right? Like this, different directions, right? So that is how. So simply these are the factors that keep the latex system stable. So we will consider one rubber particle, right? So this is the rubber particle. So because of the proteins, you can see negative charges on the rubber particle, right? If there are negative charges on the rubber particle, the next layer is a water layer, which comes from the uh, water absorbed from the soil, right? And which is available in the plant, right? So that is the water they are in around the rubber particle, right? So the surface is negatively charged. Then the adjacent water layer should have positive charges, right? So next to next layers, right? The next layers, right? They contain both positives and negative charges, right? Both positives and negatives, right? So combination, right? So this rubber particle can attract positive charges and negative charges, right? So if positive charges are there, so it can attract these negative charges, right? If negative charges are there, it can attract these positive charges, right? So the electric field, right? So electrostatic density of this rubber particle ends at this point, right? Ends at this point. So it cannot attract any positive or negative charge beyond this layer, right? Beyond this limit, right? Beyond this limit, right? Okay. So here, this is the rubber surface, the rubber particle surface, and this layer is called the stern plane. Stern plane. This is the surface. The next layer is the stern plane, which contains the opposite charge, right? Is it clear to you? It's like sun, right? Sun is here, right? And what is the the last planet which has some attraction, right? Which has some attraction to the sun? Beyond that, there is no any, right? After the ninth planet, there's no any, right? If Pluto ඉන්නවා කියලා හිතුවොත් හරි. but Pluto ගෙන් එහාට නැහැනේ. Then that field is limited within particular area, right? So beyond that, that field not work, right? The same thing happens here, right? So this is called the stern layer or stern plane, right? So then after the stern plane, I told that, so there is a positive and negative charge combination, right? Within this electric field, right? Within this electric field, right? So this is called electrical double layer because positive and negative charges both are there, right? Therefore, double layer. So simply we call it as diffuse layer or double layer, right? Now you know this is the surface, it is negative. Next layer is the stern plane, which is the opposite charge, right? Next to that, the electrical double layer, which contains both charge combination. Okay. Okay. So you know the beauty, right? So earlier we learned that rubber particles are moving here and there in the latex system. Rubber particles are moving here and there. But here I will say, not the rubber particle, but all this complex, right? Charges move with the particles as it travels through a medium due to Brownian motion, right? When the rubber particle moves, these charges are also moved with this rubber particle, right? These charges are also moves with this rubber particle, right? Okay. Did you understand that? Then if somebody says rubber particles are moving here and there due to Brownian motion, you should know not only the rubber particle, but also the attached charges, right, within the diffuse layer, right? All this section is moved here and there due to Brownian motion, right? So this limit of this electric field exerted by these negative charges of the rubber particle is called the slipping plane, right? Slipping plane, right? That is the boundary of this electrical double layer, slipping plane. It's like the ellipse of Pluto, right? Within that, the gravitational field is there of the sun, right? The gravitational field of the sun is there available, right? Within the sphere of the or the ellipse of the Pluto, right? Beyond that, there's not, right? So then we can consider that ellipse as the slipping plane of this solar system, right? Like that. So this is the slipping plane of this particular rubber particle, right? So we measure the Zeta potential, right, considering this slipping plane, right? We'll see how to do it. And also it is called shear plane also, right? Shear plane, both names are there, right? Okay, and let's come to the Zeta potential, right? So why Zeta potential is important then? So to define the stability of a particular system, right, it is not enough knowing the surface charge or surface charge density, but it is important to know the potential of the stern plane, because the particle, when the particle moves, right, the adjacent layers containing charges are also moved with that particle, right? So then if we think of that particle, that is not exactly that particle, right? The particle plus the adjacent charges, right, charge layers, right? So therefore we have to consider this section, right, not only this particle, right, this section, right? Okay, see, surface is negatively charged, right? So then the stern layer should have the opposite charges, positive, right? So then this is the limit of the diffuse layer. So then that is the slipping plane, right? So when the distance is increased from the surface of the particle, right? When we increase the distance, right? Here we can see the highest potential, right? Here somewhat, right? Here little to that. When it goes there, right? So when you increase the distance, you can see the potential is decreased, right? Potential is decreased, right? You may have learned these under electrical fields or gravitational fields in your A levels also, right? So in the surface, so this is called surface potential, right? Measured in millivolts, surface potential, right? The potential energy or the voltage of the stern layer is called the stern potential, and the slipping plane is called the zeta potential, right? Zeta potential, zeta potential, right? The voltage at the edge of the slipping plane with respect to the bulk medium, is called this zeta potential, right? If adjacent particles, right, think of another particle, right? If adjacent particles have high zeta potential with same sign, right, with same sign, maybe positive or negative, no agglomeration due to electrostatic force. So you cannot find an agglomeration, right? It is simply, if you have a same particle like this, right, if same particle like this, so it's available here, right, they will not merge because of this same zeta potential. Here the zeta potential may be some value, maybe let's say 10 millivolts. If the other particle has also 10 millivolts, both are plus, right? So then there's a big repulsion, electrostatic repulsion, and they cannot come together, right? So system is stable, right? So then you can measure the zeta potential, and if you know the zeta potential, you can directly predict that the system is stable or not. Did you understand that? Now up to this point, what you learned, all the things are qualitative. All things are qualitative. You know the particles are negatively charged, right? So there are repulsions, right? And because of that, so repulsions are occur due to electrostatic forces, right? So van der Waals attractions are not considerable, right? Considerable enough to merge the particles, right? Those are qualitative. This is where you measure them. This is where you measure them, right? So we have values. We can measure the zeta potential, right? And by looking at that values, we can directly and exactly uh, predict or conclude whether the system is stable or not, right? Did you understand that?
Yes, sir.
Okay. Others?
Yes, sir, we do.
Yeah. So I will record this session, right? So you can have that video also, right? You can repeat it, then you will get more idea, right? Okay. Then how to measure this zeta potential, right? So to measure this zeta potential, you have to use laser Doppler electrophoresis method, right? Laser Doppler electrophoresis method, right? So what is laser Doppler electrophoresis? LDE, right? Simply, we can have a sample of latex, right? So we can pass laser rays through that, right? And do some calculations. So it will be automatically done by the instrument. Then it will give you the zeta potential value, right? Finally, you will get a zeta potential value, right? Based on that, you can predict what has happened in the system and how, to what extent it is stable, or to what extent it is not stable. Like that, you can predict everything, right? We'll see how it is done. Here you have the link, right? So you can refer this one. I got it from the science direct, right? So you can, if you use this link, you can find that article and you can read it, right? Okay. So here you can see a light source, right? So we can pass that light source there, right? So then it will come through this sample, right? So then why we divide this light source into two, right?
To measure
So
the
yeah,
absorption
so this should
difference.
be the reference, right? This for the reference, right? Okay, very good, right? So here we have to use these equations also to calculate the zeta potential, right? Which is this zeta, right? So charge particle velocity is proportionate to their zeta potential. So that is the basis for LDE. If the charge particles are charged, right? Uh, so their charge density, right? Charge density or the zeta potential is directly proportionate, right? Directly proportionate to their velocity, right? So their velocity, right? So particles with zeta, high potential, so they move faster, right? They move faster, right? And vice versa. Vice versa means the other way around, right? If the particles has low zeta potential, they move slowly, right? They move slowly, right? Okay, we can illuminate these particles by laser, right? We can illuminate those particles by laser, right? Then we can quantify their velocity, right? So this is an indirect measurement, right, of the particle speed using Doppler frequency shift of the scattered light, right? So light is scattering of this the scattering of laser light occurs due to the particle's speed, right? So then based on the speed, we can calculate the zeta potential indirectly using these equations, right? Here you can see this nu is the frequency shift, right? UE, so it is the particle's velocity. Here, this is the particle's velocity, and lambda is the wavelength of the laser light, right? Theta is the scattering angle, right? Is the scattering angle, right? Okay. To calculate the particle velocity, right? If you know the particle velocity, right, we can calculate the zeta potential, right? These are the factors, right? We will learn this, right, later. Okay. So this is called the Henry's equation, right? Henry's equation. So zeta potential is a physical property of the material, right? All solid liquid and liquid colloidal systems show zeta potential. So if somebody asks you to find zeta potential of a liquid air, right? But it doesn't follow this, right? But solid liquid and liquid colloidal systems, you can apply this zeta potential, right? So how Henry equation calculate this zeta potential, right? So you know UE is the electrophoretic mobility, right? Particle velocity means electrophoretic mobility, right? And this is called epsilon, right? It is the dielectric constant, right? So all those are measurable, right? And this is zeta potential, what we need, right? Zeta potential, right? And we should know the viscosity of our system, right? So how do we measure this viscosity of our system? So it is a liquid system, right? Rubber particles in water, liquid colloidal system. So how do we measure this viscosity? We can use Brookfield, right? You know Brookfield, right? And this one is a function, right? It is called Henry's function. So it is well defined. So the system, the calculation, for the calculation, we can directly take it. So normally it can be 1, right? Okay. So here you can see units of K are reciprocal length of the thickness of the electrical double layer, right? Here, so this is the length of the electrical double layer, right? So this is 1 over K. 1 over K is the K constant that we take. So it is called the Debye length, right? Electrical double layer thickness. So we have to take 1 over K there, right? So A is the particle radius, right? Particle radius. And you know, Ka, the ratio of particle radius to electrical double layer thickness, right? So here the function Ka, if Ka is the ratio between the radius and the thickness of the electrical double layer, right? So there are polar mediums and non-polar media, right? In polar media, so maximum value of this function can be 1.5, right? 1.5 means the thickness of the double layer is less in polar media, right? In non-polar media, the thickness of double layer is high, right? So this Henry's function can be 1, right? Okay. Then we'll see how to measure it, right? So there are specific cells to measure this zeta potential, right? So you can see this is the cell that we fill our colloidal system here, right? And we have to apply electrical field using these electrodes, right? You can see positive electrode and negative electrode here, right? Actually, this is a capillary tube, right? To this capillary tube, we have to fill our sample, right? And this is the zeta potential instrument, right? Zeta potential instrument, right? So here one brand, right? Malvern Zeta Nano ZSP, right? Okay, so we can load the sample here and measure the zeta potential, right? So in this instrument, you can see laser light is there, right? So we have to pass that laser light here, right? Then divide into 2 beams to find the reference, right? To find out whether there are noises, right? So, and we can tear the instrument, right? Means calibration, right? We can calibrate the instrument, removing all the noises, right? Now the instrument is ready to measure. Then we can pass this light through our colloidal system, right? This cell is this one, right? This is the cell, right? So then light will pass, so it will indirectly measure the scattering, right? So when light hits the particles, based on the velocity of the particles, this light will scatter, right? Scatter into different direction, right? So based on that scattering, right, we can convert that frequency shift into electrical mobility, right? So then, so this is the data we can obtain for the mobility, right? We can obtain for the mobility, and we can convert this mobility into zeta potential using Henry's equation, right? Using Henry's equation. Okay. But the zeta potential, we should know, it depends on the pH and salt content of the system, right? Let's say if we take the rubber latex from Matale or Kegol area, right? And Agalavat area. So in Agalavat area, water is very good, right? Water quality is very good, right? So iron content is somewhat less. But if you take latex from Matale or Kegol area, you can see that soil series is called Parabe series, right? Which contains high calcium and sometimes I can't exactly remember. The potassium is available highly in Kegol area, but I'm not sure, right? I can't remember exactly, but I know in Matale area, the calcium and magnesium level is high, right? So then those are the salts, right? If you take the zeta potential of Agalavatta rubber latex and Kegol, right, there may be difference, right? And sometimes people may add some, sometimes people add urea, right? Urea means what? Urine, right? So they can add urine to latex to increase the density. So then they can have high metrolac value, right? Then they can have some more money, right? So, so based on those also, the zeta potential can be changed, right? So then we can use the zeta potential to identify whether the latex is adulterated, right? So we can do many kind of research with this zeta potential, right? Latex quality and colloid stability, right? Different things, right? But when you report the zeta potential, you have to mention the pH and the salt content of this material, and also viscosity and what we discussed here, right? Dielectric constant, those things, right? So to elaborate the zeta potential very well, it's like defining pH. When you define pH, if I say the pH of this water what I am drinking is 7, will you agree with me? Is it scientific? It
No,
is
sir.
not scientific, right? I have to mention the temperature because the pH is a temperature dependent, right? So at room temperature, now the temperature is 27 here. This water has a pH around 7, right? 7.1 like that, right? So it is more elaborative, right? Okay, then we can measure the zeta potential. So here you can see this sample has negative zeta potential, minus 40, 50, 60 like that, no? 70 or 60 like that, right? Minus a minus value, right? Okay, then what is isoelectric point? IEP, isoelectric point. So isoelectric point is the pH at which the net charge of the system becomes 0. Net charge of the system becomes 0, right? The pH at which the zeta potential is 0, or at which the net charge of the system is 0. So net charge of this, all the positives are equals to negative, right? So net charge is 0. When the net charge is 0, particles cannot move, no repulsions, right? So they will slowly come closer and they will merge and settle, right? They will merge. That is coagulation. So what is the isoelectric point of latex at room temperature? Yes. What is the isoelectric point of latex at room temperature? It is around 4.4 pH. It's around 4.4 pH. Actually, that pH is this isoelectric point, right? 4.4, right? If you have acidic surfaces, right? The isoelectric point for acidic surfaces is below pH 7, right? And basic surfaces is higher to the pH 7, right? Okay. So where the zeta potential becomes 0, the pH at that point is called the isoelectric point, right? Isoelectric point. Where the zeta potential is 0, at that point, the pH of the system is taken as the isoelectric point, right? Did you understand that?
Yes,
Yes,
sir.
sir.
Yeah. Okay. So then, this one example I took from research paper, right? So they have used low ammonia TMTD zinc oxide preserved latex and epoxide natural rubber latex and maybe concentrated epoxide natural rubber latex, right? However, there are 3 latex samples which are different each other, right? So this is the pH of the sample, right? And they have measured the Zeta potential, right? They have measured the Zeta potential, right? So at pH around 1, right? Around 1, the Zeta potential of this epoxide natural rubber is around plus 20 or 20 here, maybe 30 here, 25 something, right? 25 something plus 25, right? So when we increase the pH of this epoxide natural rubber latex, when we increase the pH, to increase the pH, you have to add some bases, right? If you want to increase the pH, pH එක වැඩි කරන්න නම් bases නේ එන්න ඕනනේ. හරි? Increase it, right? So the Zeta potential is getting reduced and becomes 0 at this point, where the pH is around 2.5, let's say 2.5, right? So then Zeta potential of this one is, sorry, isoelectric point of this latex is epoxide natural rubber is around 2.5 at a given temperature, right? At a given temperature, right? Okay. Then for this one, concentrated, that cannot be concentrated, that should be carboxylated, right? This C is for carboxylated. Carboxylated epoxide natural rubber, right? Carboxylated epoxide natural rubber, right? Earlier, the Zeta potential is plus 40 millivolts. When we add some bases, right? So the pH is maybe around 3.2 like that, right? Isoelectric point is 3.2 something, right? At a given temperature, right? So here around 20, no? Low ammonia, right, around 20, and isoelectric point is 4.1, like that. 4.1. Okay. So if I say all these are preserved latex, right? Low ammonia, epoxide, carboxylate. So normally we know the latex particles are negatively charged, right? So to preserve these, what we have to add? Bases, no?
Yes, sir.
Bases, right? So these are already preserved systems, right? So at the beginning, their pH may be around here, 10 to 11 at the beginning, right? At the beginning, their pH may be here, 10 to 11, because of the bases added, maybe ammonia, potassium laurate, potassium oleate, right? Any kind of thing, right? Because these are synthetic latex, we use soaps, right? So soaps have high pH, right? Potassium oleate, and or else we use KOH, right? KOH and soaps. Okay. Now I will take this one, low ammonia TMTD preserved latex, right? So I will add acids. Which acid you prefer? Formic, right? I am adding formic. So then what will happen when I add formic? The pH will drop, right? pH will drop little by little, right? So when pH drops, the Zeta potential will not change up to this point, right? It is not almost changed, right? You can see it is almost similar, right? May have written ගොඩක් වෙලාවට Zeta potential ගොඩක් similar. What is the range? Minus 40, right? Zeta potential is minus 40. Although I add acid, zeta potential is still minus 40, right? Still around minus 40 to 50 like that, no? Minus 50, right? මේ 40 50 අතර තියෙනවා නේද මම ඔච්චර ඇසිඩ් දාවත්.
Yes, sir.
Yeah. So up to 5 even. 5.75 like that. Right? මේ වගේ නකම්ම මේක stable තියෙනවා. It is stable. Right? Zeta potential is a high minus value. Right? High minus value. Right? Beyond 40. Right? And beyond 30 even. Minus 30 even. Right? Beyond minus 30. So it is stable. It is more stable. After passing this pH value, now when I add acid furthermore, right, you can see a dramatic increase in zeta potential, right? And it becomes 0 at this point, at this pH value, right? Where the coagulation is take place, right? Where the coagulation is taken place, right? If I further add acids, right, further add acids, so if I do this slowly, right, if I do this slowly, all the latex particles will coagulate at this point, and beyond that it is a solid material, right, a solid lump, right, a coagulated rubber lump, right, solid rubber. But if I do this quickly, or else instead of adding formic, I will add sulfuric, concentrated sulfuric, and I will do it quickly, or else formic acid I will add it suddenly. I will add it suddenly. So then this pH will drop to this point and the particles will, so then let's say, let me to explain in this way. So these are negatively charged, right? So when I add positive charges, the acids, right, all these will diminish at this point, right? Then those negative charges will be replaced by positives, right? Will be replaced by positives. If I add furthermore, right, if I add acid furthermore, this charge density will further increase, right? This charge density will further increase, and it will take a positive zeta potential value. Now we call this as a positex. It is positex. Earlier it is latex, now it is positex. But after, if I do this slowly, at this point it will coagulate, right? It will completely coagulate. Later I will add acid, right? But that it will decrease the pH value of the water phase, right? And not the zeta potential of the rubber. It is already coagulated. Can we increase the zeta potential of the coagulated material? So this is measured for liquid colloidal systems, maybe, or else solid liquid colloidal system, right? Solid liquid colloidal system. So our rubber particles are solid, so it is available in the latex water phase, right? Solid liquid system, right? It is an emulsion, right? Once all the rubber particles are coagulated, it is not already a emulsion. But here I want to explain the carboxylated one, right? So it is in blue color, right? So carboxylated. So carboxylated latex has somewhat high zeta potential value at high pH levels compared to the normal epoxide latex, right? That is due to the tethering of carboxylated compounds, right? When you carboxylate the latex, right, so you have these types of structures, right? So then you will have some high pH, high zeta potential value at the stable pH levels, right? Okay, I think it is clear to you.
So in a sample, are all the particles having same zeta potential law? So
No,
average.
it is accumulation,
Okay.
right? So this will give an average. That's why we have to run at least 3. Then we can average the average, take the mean of the mean, right? Because let's say 100 particles are there in the sample, for example, right? So those 100 have different potentials, different slipping potential, no? Right? Because this laser light measures the speed of these moving particles. Then it will be converted into the zeta potential by calculating the mobility, right? Electrophoretic mobility is converted into zeta potential, right? So then it is an average then, right? So then we have to run at least 2-3 samples, right? So we have then three averages. So we can average those 3, then taking the mean of the mean, right? So we can have a good idea, right? Did you understand that?
Yes, sir. Thank you.
Okay. Then come to this point. I think you can remember I marked minus 30 in the previous graph, right? Here, right? Because of this, right? See, rubber latex maintains colloidal stability, right? If surface charges having either lower minus 30 or higher than plus 30. Higher than plus 30 or minus 30, lower than that, right? So then to occur, the rubber latex stable, its zeta potential should be below minus 30 or above plus 30. If it is above plus 30, that is a good positive, right? So here you can remember I marked my plus 20, right? Plus 20 here, right? And minus 30 here. So minus 30. So below these pH levels, right? Below these pH levels, latex is more stable, right? It is more stable, right? Below this pH level, it is more stable because zeta potential is, right? Zeta potential is below minus 30. It is stable. But do you think when we add acids, it will becomes this point where the isoelectric point. Then although all the rubber particles are not coagulated, right? We can observe all the rubber particles are not coagulated, but 99% is coagulated, but we can see some milky serum, right? So we will add more acid there, right? Little bit more acid. So then what will happen? Some rubber particles may get positive charges, but their charge is also below plus 30, right? Below plus 30, they can coagulate because those are not stable, right? They are not stable to become positives because it has not passed the limit of plus 30, right? So they can coagulate while taking time, right? You can see some flocculation there, right? Flocculated particles with the coagulum, right? Okay, this is how you have to understand this, right? You better to read this, right? So here I have 2 sample zeta potential values of natural rubber and chloroprene rubber lattices at various pH levels are shown in figure 2. You can see the pH is here, zeta potential is here. The data indicated that the NR particle possessed positive character when pH was below 4.7. pH below 4.7 means here, right here, below 4.7. Below 4.7, NR shows positive character, right? Positive character, right? Here minus plus 30, right? But positive character, but below plus 30 means not stable, right? Keep it in your mind, right? Okay. Then above 4.7 zeta potential was negative and change rapidly with increase in pH, right? So beyond this, right, the zeta potential is negative, and when you increase it, right, so the change is rapidly changed, right? Rapidly changed, right? Okay. Then the curve in figure 2 therefore indicate amphoteric characteristic of NR. Amphoteric. What is amphoteric? NHCrHCOOH. So amphoteric. This is amphoteric. So you talk about protein layer, right? It contains this amine, which is a base, and this carboxylic group, which is an acidic nature. So both acidic nature and basic nature, both are there in one molecule, which is a protein, right? Protein molecule. So this can withstand against acids and against bases, right? Because of that, we can say this shows positive and negative both, right? Positive stability and negative stability because of what? This amphoteric nature given by the protein layer of the rubber particle. Did you understand that? Clear?
Yes, sir.
Yeah, these are from A levels, right? A level වල ඉගෙන ගත්තේ මේවා. හරිද? Is it clear to you?
Yes, sir.
Yes.
Questions you can raise, right? The results confirm the presence of amino acids at this, right? So what I explained, right? But you can see the chloropene latex, right? Chloropene latex, zeta potential showed the negative value of the range of pH. See, it is negative over the range of pH. No positive, no amphoteric nature there, right? Okay, so this is because of what? Negatively charged, possibly derived from the anionic surface. So this is the chloroprene, right? So this is a synthetic lattice. Synthetic lattice. So for the synthetic lattices, we use anionic surfactant. මගේ අකුරු ගැන එච්චර දුක් වෙන්න එපා ඒවා එහෙම තමයි. මම ආසත් නැහැ ඒක හදලා ආයෙ ලස්සනට ලියන්න. හරි? ඔයාලට ඕනනම් කොලේ අරන් ගිහලා ෆාමසි එකකින් අහගන්න. හරිද? Chloroprene rubber synthetic. It is a synthetic one, so we have to use anionic surfactants, right, to stabilize the system, right? So it shows negative zeta potential over the range, right? If we further reduce the zeta potential, the pH, right, it will become here, right? It will become here, and sometimes it will get zeta potential 0 at this point, right? So it has not given in this paper, but up to this point it has given, right? Okay, but it is more enough, right? More enough to unstabilize the system if you get it here, no? -30 වලට උඩට ගෙනාවත් ඇති ඒක unstable වෙනවා, right? With the time it will coagulate, right? Okay, this is another example where what will happen. So effect of electrolyte on double layer thickness K, which is 1/K Debye length, right? Concentration of 1:1 electrolyte in water at 25 Celsius. You can see everything is explained well, temperature and concentrations, then ratios. Okay, what will happen? So here we are going to add this particular electrolyte, right? So we are going to add acids, right? Let's say acid. If this is, you can think of this is natural rubber, right? We can add acids. So when we add acids, what will happen to these negative charges, right? So this is the concentration of the acid, right? -5. Which one has the lowest concentration? This one or the last one? The first one or the last one? The highest concentration?
Last ones.
Last one.
Last
Yeah.
one.
Last answer.
Yeah, it is the highest concentration, right? High. high concentration, right? Here low concentration. So at low concentration, right, you can see the double layer thickness is high. When you increase the concentration of your electrolyte, right, you can see double layer thickness is getting reduced because of the reduction of charge density, right? So then the next one can come closer, right? When the Zeta potential becomes 0, right, they will merge and coagulate, right? If it is latex, pH is 4.5 like that, 4.5, 4.4 like that at room temperature, right? Okay. These are the reference. You can find some more information if you follow these references.